Our senses tell us a simple story. They paint a picture of a world that seems straightforward and easy to understand. We live in a world of three dimensions: up and down, left and right, forward and backward. These are the axes that define our physical reality, the coordinates that map out our existence. But what if our senses are only revealing a sliver of reality? What if there is more to the universe than what meets the eye? Imagine a tapestry woven by a cosmic loom, a fabric of existence with threads extending into dimensions beyond our perception. Each thread represents a different aspect of reality, intertwining to create the complex and beautiful pattern of the universe. This is the tantalizing possibility offered by the idea of a four-dimensional universe, a realm where time and space are interwoven in ways that challenge our understanding. We are like shadows, trapped on the surface of this grand tapestry. Our movements and experiences are confined to the three dimensions we can perceive. Our everyday experiences play out in a three-dimensional projection of a higher reality. We navigate through life, unaware of the deeper layers that lie just beyond our reach. The fourth dimension, hidden from our direct view, holds the key to understanding the universe's deepest secrets. It is a realm where the familiar rules of physics may no longer apply, where new possibilities emerge. But how do we even begin to grasp such a concept? How can we, with our limited senses, comprehend a dimension that we cannot see or touch? Mathematics provides the tools and the language. It offers a way to describe and explore dimensions beyond our immediate perception. It allows us to explore the terrain of higher dimensions, even if we can't directly experience them. Through mathematical models and equations, we can visualize and understand the properties of these hidden realms. Through the lens of mathematics, we can glimpse the intricate patterns and hidden connections that govern the cosmos. We can see how the threads of the tapestry are woven together, revealing the underlying structure of reality. We can begin to unravel the tapestry of the universe and explore the dance of dimensions. By expanding our understanding, we open the door to new discoveries and a deeper appreciation of the cosmos. What exactly is a dimension? This question has intrigued scientists, philosophers, and curious minds for centuries. Dimensions are fundamental to our understanding of the universe, yet they remain one of the most abstract concepts in physics. In the simplest terms, a dimension represents a direction of movement. Imagine walking along a straight path. This path represents one dimension. In our familiar three-dimensional world, we have the freedom to move in three independent directions. These directions are the axes along which we navigate our daily lives. We can move up and down, left and right, or forward and backward. Each of these movements is distinct and independent of the others, allowing us to explore our environment fully. Each of these movements is independent of the others. Think of how a child plays in a playground, moving freely in all directions, unconstrained by any single path. They are like the threads of a tapestry, woven together to create the fabric of space. Each thread represents a possible direction, and together they form the intricate pattern of our reality. But what if there were more threads, more directions in which we could move? This idea opens up a realm of possibilities that extend beyond our everyday experience. This is the essence of higher dimensions. Higher dimensions are not just theoretical constructs, they are a fundamental part of many advanced scientific theories, including string theory and quantum mechanics. A fourth dimension would be an additional direction, perpendicular to all the directions we know. Imagine a new axis, one that we cannot see or touch, but that exists nonetheless. It's a mind-bending concept, difficult to visualize because we are so accustomed to our three-dimensional existence. Our brains are wired to understand the world in three dimensions, making the idea of a fourth dimension almost alien. To grasp the idea, imagine a flat, two-dimensional being living on a piece of paper. This being can only perceive length and width, but not height. This being can only move left and right, forward and backward. Its entire existence is confined to the surface of the paper, much like how we are confined to our three-dimensional space. It has no concept of up or down. The idea of moving in a direction perpendicular to its plane of existence is beyond its comprehension. Now imagine a three-dimensional object like a sphere passing through the paper. To the two-dimensional being, the sphere would appear as a series of changing circles. First a small circle, then a larger one, then shrinking back down until it disappears. This sequence of circles is the two-dimensional being's limited perception of the three-dimensional sphere, then shrinking back down until it disappears. The two-dimensional being would only experience a slice of the sphere at any given moment. The two-dimensional being would only experience a slice of the sphere at any given moment. it wouldn't be able to perceive the sphere's true three-dimensional nature. Similarly, we are limited in our perception of higher dimensions. We are like that two-dimensional being, only our paper is the three-dimensional universe we perceive. The true nature of reality might be far more complex than we can imagine, with dimensions beyond our current understanding. To navigate the realm of dimensions, mathematicians use the concept of vector spaces. A vector space is like a grid that extends into any number of dimensions. Each point in this space can be defined by a set of coordinates. In our familiar three-dimensional space, we need three coordinates to specify a point's location, its position along the x-axis, the y-axis, and the z-axis. In a four-dimensional space, we would need four coordinates, and so on. Vectors are like arrows that connect points in this dimensional grid. They have both magnitude, length, and direction. Vectors allow us to describe movement and relationships within a vector space, regardless of the number of dimensions. Vector spaces provide a powerful tool for exploring higher dimensions because they abstract away the need for visual representation. We can work with the mathematics of four-dimensional vectors, even if we can't picture a four-dimensional object in our minds. This is the beauty of mathematics. It allows us to transcend the limitations of our senses and explore realms that would otherwise be inaccessible. Section 4. Tensors, the language of curved spacetime. While vectors are useful for describing straight lines and flat spaces, the universe is anything but flat. Our cosmos is a dynamic, ever-changing tapestry of matter and energy, woven together in a complex dance. The landscapes we see on Earth, with their hills, valleys, and mountains, are just a small reflection of the intricate curvature that exists on a cosmic scale. Einstein's theory of general relativity tells us that gravity is not a force, but rather a curvature of spacetime itself. Imagine spacetime as a flexible fabric. When a massive object like a star or a black hole is placed on this fabric, it causes a dip or a curve. This curvature is what we perceive as gravity. Objects moving through this curved spacetime follow paths dictated by the shape of the curvature. To describe this curvature, we need a more sophisticated mathematical tool: tensors. Tensors are not just abstract mathematical constructs, they are essential for translating the complex geometry of spacetime into a language that physicists can understand and use. They allow us to quantify the curvature and understand how it affects the motion of objects. Tensors are like vectors on steroids. While vectors have magnitude and direction, tensors can have multiple components, each representing different aspects of a physical quantity. This makes them incredibly powerful tools for describing the properties of spacetime. They can be thought of as multi-dimensional arrays of numbers that describe the properties of physical quantities at every point in space and time. Imagine a grid overlaying the universe, with each point on the grid containing a set of numbers that describe the curvature of spacetime at that location. This is essentially what a tensor does. For example, the curvature of spacetime caused by a massive object like a star or a black hole can be represented by a tensor. This tensor encapsulates all the information about how spacetime is distorted by the object's mass and energy. This tensor tells us how much space and time are distorted at each point in the object's gravitational field. It provides a detailed map of the gravitational landscape, showing how objects will move and how light will bend as it passes through the curved spacetime. Tensors are essential for understanding the universe on the largest scales, because they allow us to describe the complex interplay between gravity, matter, and the fabric of spacetime. Without tensors, our understanding of the cosmos would be incomplete, and many of the phenomena we observe would remain mysterious. They are the language of general relativity, and they provide a glimpse into the mind-boggling geometry of the cosmos. Through tensors, we can begin to unravel the secrets of the universe, from the smallest particles to the largest galaxies, and understand the fundamental nature of reality itself. Section 5. Shadows and Projections. Glimpsing the fourth dimension. Even though we can't directly perceive the fourth dimension, we can still get a sense of its existence by looking at how four-dimensional objects would appear if they were projected into our three-dimensional world. Imagine a hypercube, the four-dimensional equivalent of a cube. A hypercube has 8 cubes as its faces, just as a cube has 6 squares as its faces. If a hypercube were to pass through our three-dimensional space, we would see a series of changing cubes, appearing, disappearing, and merging in strange and unexpected ways. This is analogous to the two-dimensional being seeing a series of circles when a sphere passes through its plane. The changing shapes we would observe are just shadows, projections of the hypercube's true four-dimensional form. By studying these shadows and projections, mathematicians and physicists can learn about the properties of higher-dimensional objects, even if we can't directly experience them. It's like trying to understand the shape of a sculpture by looking at its shadow cast on a wall.